Hello, this is Mr. Henry, and welcome to Lesson 5.3, Linear and Nonlinear Functions. The essential question says, how do I determine if a function is linear or nonlinear? Seems fairly straightforward if you know what linear and nonlinear means. The warm-up is a type 1 with 2 minutes on the clock, and it says, list 2 things you know about functions and 1 question you have about functions. So we've had 2 lessons now. You should know something about functions in the past 2 lessons we've done. The first lesson is what is a function and how to identify it. The second lesson was how to compare functions. So you should know what a function is and how to compare a function. What's a question you might have about a function? Well, that one you have to come up with on your own. Go ahead, pause the video. When you're ready to move on to the vocabulary, hit play, and we will move on. So we have 2 vocab words here. We have linear function and nonlinear function, which, if you remember the title of the lesson, how do I determine if something is linear or a function is linear or nonlinear? Well, first off, you got to know what linear and nonlinear are. A linear function is a function whose graph forms a straight line. The slope remains constant. So this word, linear, see these first 4 letters? Spells the word line. Something that is linear is in a straight line. So a linear function is something that looks like that. And it said here, the second part, the slope remains constant. That does come into play throughout the lesson. So between any 2 points on a line, if this goes like, say, oh, that was terrible. Say up 3 over 5. Well, if you'd find the slope of the next 2 points, it would again be up 3 over 5 the whole way. You're never going to find a place where it goes over here and it's like up 3 over 7, because that would mean that it went higher up or went further off to the side. Okay, so something that is linear has a constant slope. The slope does not change. Now, being the smart, intelligent people we are, you could probably take an educated guess at what something that is nonlinear would look like. A nonlinear function is a function that, when graphed, does not form a straight line. So a nonlinear function, to give an example, is like that. That is a function. If you remember the definition of function, the vertical line test, it passes the vertical line test. So it is a function, but it's not linear. It's not a straight line. It's a curvy line. See, it can be increasing or decreasing, or both increasing and decreasing. This function I drew here is increasing and decreasing. This is both. One that's just increasing but nonlinear could be like this. This is not linear, but it's just increasing. It's not linear, but it's just decreasing. Okay? So we're going to learn how we can determine if something is linear or nonlinear. And the one point about this vocab that I wanted to mention here is it says when graphed. A function whose graph forms a straight line. A function when graphed does not form a straight line. But all the stuff we're going to see here today is not going to be graphs. So we're going to need some other methods to determine if it's linear or nonlinear besides looking at a picture of it. Okay? So let's go ahead and get started. It wants us to determine if each relation, it says here, each relation shown is a function. Is the function linear or nonlinear? If it is linear, identify the slope and the y-intercept. Okay, so I'll be giving you functions in various forms, tables, graphs, equations, and we have to determine if it is a function. If it's a linear function or a nonlinear. So I guess the question comes down to, what's the difference between linear and nonlinear? Linear, nonlinear. Well, hopefully you remember the word linear is a line. And nonlinear would be not a line. Or we should say straight line. So a linear function will form a straight line. Those are the equations typically in the form y equals mx plus b. This is the equation of a straight line where that is your slope and that is your y-intercept. So what we're going to do today is to determine if an equation is linear, we're going to see if we can write the equation in that form. If we cannot, that probably means it's not linear. If we can, then that means it's linear. So let's take letter A, for example. We want to write this in slope-intercept form, which means we want to get the y variable by itself. So let's try that. So to get the y variable by itself, we're going to subtract 2x. We're trying to make this slope-intercept form. Y equals negative 2x minus 15. All right. Were we able to write the equation of this line in slope-intercept form? Y equals mx plus b. Absolutely. This is linear. It's linear because we were able to write it in slope-intercept form. That makes it the equation of a line. All right. And it says if it is linear, identify the slope and the y-intercept. Okay, so slope and y-intercept. Now, because we wrote this equation in slope-intercept form, these next two questions are very easy because the slope, well, in slope-intercept form, this is your slope and that is your y-intercept. We're done. All right, letter B. Now, you probably saw this one already and made your guess. Do you think letter B is linear or non-linear? The answer is non-linear because it's not a straight line. It has curvies in it. You can't have these curvies like this. It has to be just a straight line. It could be up, it could be down, sideways, flat, whatever. But the fact that we have this curve going on here makes this not a linear function. So this function is non-linear. There we go. And that problem is done because it says in the directions, if it is linear, find the slope and the y-intercept. Because this function is not linear, the slope would be different depending on where you picked it. So if you picked, a small section right here, the slope would be like this. If you picked a section like over here, the slope would be going down like that. So this does not have a consistent slope. It's not linear. Letters C and D. Now, these two are both tables. And we're still trying to figure out if this is a linear function or not. Well, something I said just in the last problem, letter B, I think will help us a lot here. Because I said something like, here the slope would be different than there. The only way this would be linear is if the slope is the same everywhere. So if we find the slope of a couple different places on this, so if I maybe find the slope of these 2 points and those 2 points, if the slope stays the same, it would be linear, because for the slope to stay the same, you'd have to be going on the same straight line. So everywhere on the slope, if you pick 2 points here, you get whatever slope that is. You pick 2 other points, you get the exact same slope. The only way the slope would be different is if you're curving, and then the slope between here is different than the slope over there. So that's what we're going to try to do. We're going to try to take these tables, and we're going to find the slope at a couple different points. If the slope is the same, that means you're on a straight line. If the slope is different, that means you're on a curvy line. Okay? So slope formula, m equals y2 minus y1 over x2 minus x1. So let's see here. I'm going to use these 2 points. So x1, y1, x2, y2, -5 minus -8 over -2 minus -3. That gives me, see, keep, flip, change, keep, flip, change, +3 over +1. All right, so from right here, I got a slope of 3. If down here I get the same slope, that's a pretty good sign that this would be linear. If I get a slope that's not 3, that would mean it's not linear. So let's check. My new x1, y1, x2, y2. So I take 16 minus 4 over 5 minus 1. Let's see, 16 minus 4 is 8. No, 12. 5 minus 1 is 4. And 12 over 4 simplifies to 3 over 1. Ah, I got the same slope. So I got the same slope here as I did there. Now, the chances of these being the same slope coincidentally, even though if the equation is not linear, is very low. So the fact that I got the same slope at 2 different places means that this is probably linear. I would put my money on it, and I'd say this is a linear function. If you're unsure, you can continue to try other points, other pairs. So we tried the 2 that I have marked. You could try, maybe like this guy and that one. If you did 4 minus 1 over 1 minus 0, you get 3 over 1. So that also has a slope of 3, and you could try like that one and one down here. You'd find that has a slope of 3. So this is a linear function, because the slope is constant everywhere. It has a constant slope, so it's a straight line. Letter D. We'll do the same deal. I'm going to pick 2 points, and maybe those 2 again, and I'm going to find the slope. If the slope is the same, it's linear. If the slope is not the same, it's not linear. So x1, y1, x2, y2. So I have my equation up above here. So we got 0 minus 12 over -2 minus -4. Keep, flip, change. Gives me -12 over a +2, which is a slope of -6. All right, so far, between these 2 points, I found a slope of -6. Now we're going to use the bottom 2 points. So my new x1, y1, x2, y2, we'd have x2 minus x1 over y2 minus y1. Let's see. Down here I'm going to get a 2 again. 21 minus 15 gives me 16. That gives me a slope of a +8. So here I got a slope of -6. Here I got a slope of +8. So at this earlier point, the slope is really negative. This later point, the slope is really positive. So the only way that's going to happen is if this is not linear. So there's my negative slope. There's my positive slope. This is not linear, because the slope did not remain constant. It was not a straight line. It has to be curvy for us to get 2 different slopes. Oh, I almost forgot something from letter C. It says if it is linear, identify the slope and its intercept. Okay, so we found the slope. The slope was 3. We did that. I almost missed that. The slope is 3. There it is, there it is, there it is. So what's the y-intercept? Well, back in the day, way back lesson 4 point something something, what we did was, if we had a bunch of points, we used this thing called point slope form, which was y minus y1 equals m, x minus x1. And then if we had to write the equation in all of our different forms, all we did is we plugged in our slope for the m and one of our points for the x1, y1, and then we could solve this into slope-intercept form to find the intercept. I'm guessing that's what we should do again. So let's do that. Let's take in our slope of 3 and pick a point. Now, I'm going to pick this point. That was bad circling. I'm going to pick that point right there because those numbers are both small. 0, 1. I don't like the negatives. I don't like the super big positives. I like that. So I'm going to plug in when x is 0 and y is 1. And if I can change this into slope-intercept form, which is y equals mx plus b, then I'll be good. So let's see. We've got to get rid of those parentheses. So we distribute 3x and 3 times 0 is just 0. So I don't need that. And then to get this y by itself, if we add 1 to both sides, y equals 3x plus 1. This is slope-intercept form. So right there is my slope, and right there is my y-intercept. So the slope is 3, and the y-intercept is 1. So that's how you find your slope and your y-intercept from just a set of points. We found the slope using slope formula. We plugged that into point slope form. We then solved into slope-intercept form. So there's the slope and there's the y-intercept. Letter E. It says here each relation is a function. So it's the same information. Is a function linear or nonlinear? And if it is linear, identify the slope and the y-intercept. All right, so letter E. Well, again, if we have an equation, our goal is to make it look like y equals mx plus b. If we can do that, then it is linear, and we can do all this other stuff like finding the slope and the intercept. So let's see. If we so we gotta get the y by itself. If we add 4x cubed, and that's kind of weird, this cubed thing. 4x cubed. 2y equals 4x cubed plus 16. And then if we divide by 2, y equals, let's see, 4 divided by 2 is 2x cubed plus 8. Now, this almost looks like slope-intercept form, except for that funkiness of the exponent. It's actually because of that 3, that exponent there, that this is not linear. This would be a function that looks something more like that, roughly. Okay, so this is a cubic, has a third power on the exponent. It is not linear. For it to be linear, the power of all the variables, the x and the y, have to be 1. So this is not linear. And the way you can tell very easily, I could have said from right here, it's not linear. Because of this power, it's not linear. All the powers on the exponents have to be 1. If they're greater than 1, it's not going to be linear. Simple as that. Okay, letter F. Is it linear or nonlinear? Well, looking at it, it looks very linear to me because it looks like a straight line. If we do some counting boxes to find slope, so we've got point, 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 and I'd assume a point there. The slope looks consistent of down 1 over 3, down 1 over 3, down 1 over 3, down 1 over 3. So the slope is consistent, it's constant, which makes it linear. So I'm going to go ahead and say yes, this is linear. Oh, function, I guess. All right, and it asks us if it is linear, find slope and the y-intercept. Slope and y-intercept. All right, so the slope is Well, this down 1 over 3 stuff. So slope is down 1 over 3. Down 1 over 3. Down 1 over 3. Down 1 over 3. That's your slope. The y-intercept is where the line is crossing the y-axis. Right there, our line crosses the y-axis, and that's where we have an x, that's where the y value is 1. So this function has a slope of -1/3 and a y-intercept of 1. And if we really chose to, we could take this and write an equation very simply. Y equals -1/3 x plus 1. This is that slope-intercept form that we used over here. It's the same form, slope, intercept. That is the equation of that line. It didn't ask us to do that. I'm just giving you a little extra information. It asked us to find the slope and the y-intercept. And that's what we did. So here's letters G and H. Same bit of information. Is it linear or nonlinear? If it is linear, find the slope and the y-intercept. Go ahead, pause the video, and try these two problems right now. When you're ready to continue, hit play, and we'll go through it together. All right, so let's see what we got here. Letter G. Well, just looking at it, this guy is definitely not linear. It's not linear because it's not a straight line. It's a curve. It's a parabola would be the name of this. It's a parabola, so it's not linear. Simple as that. Not linear. Okay, so letter H. The way we did this before is we look at the slope of a couple different points. Maybe I'll use these two just to be different. So the slope formula is m equals y2 minus y1 over x2 minus x1. x1, y1, x2, y2. So if I plug it into the formula, we got, what is that? I meant to put a 7. 7 minus -3 over 2 minus 0. Keep, flip, change gives me 10 over 2, which is a slope of 5. 10 divided by 2 is 5. All right, down here, we've got my new x1, y1, x2, y2, giving me 27 minus 17 over 6 minus 4, which is 10 over 2, which is 5 again. We got the same slope. The chance of us getting the same slope on two different sets of points means it's probably linear. It's very low probability to get the exact same slope on two separate points if it's nonlinear. So I'm going to go ahead and say this is linear. Darn. Because it's linear, now we got to do some of that extra work, like finding the slope and the y-intercept. Okay, well, the slope is already done. We found that when we were figuring out if this was linear or not. The slope was 5. Okay, now the y-intercept we're going to find either using the formula, or actually I'm going to do that way first, and then I'm going to show you a little shortcut if you don't know it. So I'm going to plug in the point, or I'm going to use the formula, y minus y1 equals m, x minus x1, where the slope is 5, that's x, that's y, and this y1 and x1 come from one of the points up here, and you can choose any of the points you like. Let's choose, what, 2, 7? So I'm going to plug in 2 for my x value, 7 for my y value. And if we solve this for y, to make it slope-intercept form, that'll give us the y-intercept. So I'm going to start by distributing, giving us, what, 5x minus 10, and y minus 7. If I add 7 to both sides, that gives me y equals 5x minus 3. That is slope-intercept form, because that is my slope and that is my intercept. We're done. Now, this is the long way. The shortcut is, if you know, the y-intercept always happens when the x value is 0. If you look at my little table over here, when the x value is 0, right here, because x of 1, x of 2, x of 3, x of -1, x of -2. When the x value is 0, puts you on the y-axis. And so you can actually tell by looking at a table, if you find where the x value is 0, the y value would then be the y-intercept. So the y-intercept happens when the x value is 0. Just a little shortcut. It works actually back in the other problem that was similar to this back here. We set up our equation, we solved, and we found that the y-intercept was 1. But looky here. When the x value is 0, the y value is 1. So just a little shortcut is all. Might save you some time if you remember it. If not, this was not that much work. Took a couple steps. You do it off the side on a separate sheet of paper, but it's not that much work. Letter I. Here's one for you to try. So you're going to tell me if that is linear or nonlinear, and if it is linear, what is the slope and the y-intercept? Go ahead, pause the video, do the problem on your own. When you're ready to continue, hit play, and we'll go through it together. Alrighty. So determine if this is linear, especially since you're using an equation. You want to see if you can write this in the form y equals mx plus b. So that's what we do. Let's see. Well, if I can get this piece gone, then the rest would be in slope-intercept form. So if I make this go away, so subtract 2x from this side and on the other side, you always do everything to both sides. Y equals 3 minus 2 is 1x minus 5. Is that slope-intercept form? Yes, it is, which means this is linear. And because it's linear, now we have to find the slope and the y-intercept. All right, slope. Well, we did it in our equation. This is slope-intercept form, so the slope is 1, and the y-intercept is -5. Done. That was pretty quick and easy. Okay, so now we're into the applications. It says here, an airplane flies directly from Harrisburg to Baltimore. Mark writes a function to determine the height of the airplane as it flies. Is this function linear or nonlinear? Use words, numbers, or models to justify your answer. Numbers or models to justify your answer. Okay? What do you think? Well, if you would imagine an airplane flying, I mean, you've got airplane, wing, tail, sweet. Okay? If you'd imagine this airplane flying, it's not going to be flying like this. It's going to start and it's going to go up in the air, and then it's going to kind of level out for a little bit, fly for a while, and then when it goes in for its landing, it's going to aim back down towards the ground before it finally comes to a landing. So what I kind of drew was it goes up in the air, it flattens out for a little bit, when it goes in for landing it goes back down, and then flat. So if he's writing a function that determines the height of the airplane as it flies, there's its height from Harrisburg to Baltimore, is that a linear function? Well, heck no. I mean, the height is changing. This is the height over time. So it's going to go up. It's going to probably level out for a little while, fly at whatever altitude they're going to choose to fly at before it goes in for a landing. So its height is going to be changing throughout the flight. It's not going to be like driving along the ground the whole time. Okay, so this would definitely be non-linear. And there's a nice model that represents this information to show that it's non-linear. Its height changes with respect to time as it's flying from Harrisburg to Baltimore, and it's not changing at a constant rate. Its height is not continuously going up or continuously going down. It's non-linear. Letter B. Isabella sketches a function that passes through the points 5, -3, 2, 4, and 11, -17. Isabella believes that this is a linear function. Is she correct? Explain your reasoning. Okay, well, to figure out if it's a linear function, this is essentially going to be like one of those tables we had a second ago. So like x, y, ugly y. We have 5, -3, 2, 4, 11, -17. So determine if it's a linear function. If the slope remains constant, it's linear. If the slope is different at two different sets of points, then it's not linear. So I'm going to go through and I'm going to find the slope of maybe those two and those two. Slope formula, m equals y2 minus y1 over x2 minus x1. Yes, I say it and I write it every single time. You probably should too. So if I'm using these 2 points here, I've got x1, y1, x2, y2. I'll label it x1, y1, x2, y2, which gives me, let's see, 4 minus -3 over 2 minus 5. Keep flip change. That gives me 7 over -3. So the slope is -7/3 at the beginning. Okay, let's erase them to eliminate any confusion in a second. Okay, so now when I use these 2 points, x1, y1, x2, y2, okay, same formula, y2 minus y1 over x2 minus x1 gives me -17 minus 4 over 11 minus 2. Oh gosh, let's see. That's a -21 over, that's a 9. And if we simplify, so you can divide top and bottom both by 3, that gives me -7 over 3. Huh, we got the same slope. So here we got a slope of -7/3, there we got a slope of -7/3, which means this is linear. If we got the same slope at 2 different points, the chances are it's gonna be linear. So, is she correct? Yes, this is linear. Explain your reasoning. How about this? We'll just continue our sentence. Yes, this is linear because the slope remained constant at 2 different points. There we go. Is she correct? And explain your reasoning. Yes, this is linear because the slope remained constant at 2 different points. And if you were unsure, you could, we only have these 3 points here, but you could try different pairs, and you're going to find for all 3 of these, no matter what combination you use of the points, you're going to get the same slope of -7/3. So this is linear. And letter C. It says in the space below, make 2 relations that are linear functions and 1 relation that is a non-linear function. One must be a graph, one must be a table, and one must be an equation. So what I mean by that is, down here, you're going to make two things that are linear functions. So maybe you make the equation linear and the graph linear. That would mean you need to make the table that is non-linear. Or if you make maybe these two linear, the equation and the table, then you'd make your graph that is non-linear. So out of the three spaces provided, you're going to make two things that are linear functions and one thing that is a non-linear function. Okay? Pause the video, do this on your own. When you're ready to continue, hit play, and we'll go through it together. All right, so I'm going to be slightly different, and I'm going to give you an example of each. So if you're going to do your graph, a linear graph would just be a straight line, or as straight as you can make it. And then in blue, a non-linear graph, red, a non-linear graph would be something like that. So blue is going to be linear, and then red would be non-linear. All right? I'm going to skip the table for right now. Equation. So a linear equation would be any equation in the form y equals mx plus b. So y equals 3x plus 5. That would be linear. A non-linear equation is just an equation you cannot write in that form. So if you throw some other exponents in there, so like y equals 4x squared plus 3x minus 7, you can't write that in slope-intercept form, which means this is non-linear. Okay. To do this, I'm going to make x, y, bad x, bad y, because I'm showing both, so I need an extra little table here. So this side will be linear, this side will be non-linear. Now, the good news about non-linear, if you just make up a couple random points, the chances of the slope being the same is very low. So I'm going to pick something like 3 and 6 and 5 and 12 and -7 and 96 and 0 and 1 and 4 and 15. I don't know. I mean, the chances of this being linear are extremely low because I tried to pick numbers that were not close to each other. They're very different. I'm not going to get the same slope at any two particular points. All right. Now, this one's a little bit harder. So here's how I would do this. I would come up with just some simple little linear equation. Maybe we use this guy here. And if I say, okay, when x is 0, if I plug in 0 for x, what's my y value? 0 times 3 is 0, plus 5 is 5. Plug in 1. When x is 1, let's see, 3 times 1 is 3, plus 5 is 8. When x is 2, 3 times 2 is 6, plus 5 is 11. And 3, notice we're just adding 3 each time, 14, and 4, 17. So the blue would be linear, the red would be nonlinear. Blue is linear, red is nonlinear. Blue is linear, red is nonlinear. So I showed you one of each. Your job was to only do one of those. So if you make these two linear, then that would be the nonlinear. But I wanted to show you an example of what each of them look like. Okay, so for our summary of this lesson, we have a type 2. So I'll be grading your answer on the correctness of your response. Make sure you take your time. It says, how can you tell by looking at a graph if a function is linear or nonlinear? That is so easy. So hopefully we all get it right. How can you tell by looking at a graph of a function if it is linear or nonlinear? Pause the video if you need the question a little bit longer. If not, this has been lesson 5.3. Thanks for watching.